right? So just to recap from what we have done in the last two lectures, uh, what have we learned? Can somebody tell me what they have learned?
So tray by tray calculation, how we do it. Actually, it is done using thermodynamic model.
Okay, how to do tray by tray calculations. What else have we learned?
Calculation for multi-component.
Okay, so I can put binary and multi-component. So once you do multi-component, then binary will seem like a child's play. Any junior could do binary, isn't it? Okay, anything else we have learned?
Converting isothermal equilibrium data into isobaric equilibrium data.
Okay, so isothermal equilibrium data to convert to isobaric data. All right, great. Because isobaric data is what we need for distillation columns and things like that. Isothermal is we can easy to it's more accurate to do experiments under isothermal conditions. It's better, or it is more scientifically correct to fit the model parameters. Say for example Margulis 1 constant, it is better to fit it to an isothermal data because the temperature is constant, so the values of the parameter A does not change with composition, because the it does not, it changes with temperature, but because the data is isothermal, it is better to fit the thermodynamic constants to isothermal data. Okay, what else have we learned? Have we learned anything else, or only these two things we have learned?
Also, we could actually analyze how the number of plates decreases with increasing the R.
Right, so reflux goes up, number of theoretical plates come down. Column diameter, did you find?
No, sir. I was going to ask you, sir. Like, we don't know. I do not know how to find out the column diameter through flooding. There are different equations used. So, sir, if
Ah,
there's any method, if we could follow to
okay,
find
but
out.
okay, you will find that column diameter, we'll discuss that. So column diameter will increase. Okay, now anything else? So this we will discuss today. Anything else? Any other thing we learned? No, we didn't learn anything more. We learned only three things. Anybody else? What did they learn? I mean, what did you learn? Forget about others. Others may have learned something else, but what did you learn? Besides these three things, what else have you learned? This what you have learned. So it depends on you. What have you learned? It can be different for everybody. It need not be the same for everybody. Somebody would have learned something else. Somebody would have learned how to use Excel, how to do NRTL calculations in Excel. Maybe that you have learned. So everybody just say something, whatever you have learned. There's nothing right, nothing wrong in this. What have you learned in last two sessions? So just anything.
So using solver in Excel instead of goal
Okay.
seek.
Right, using solver or goal seek. Right. Great. Right. It's not necessarily related to distillation, but yes, it is something that you have learned. Correct. Good. What else?
In RTL using three components.
Okay. So three component NRTL. Okay. What else have we learned? Have we learned only these 3 things? 4, 5 things? One thing I don't know whether you learnt or not, but I tried to say explicitly is don't use constant alpha across the whole composition. I mean, did we learn this? Do you agree? Do you disagree?
Yes, sir.
Only one person is saying yes.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we are never ever going to use constant alpha. Better not to use alpha, but use thermodynamic models. Have we learned this? Even as simple, oops, not single, simple as one parameter model. Have we learned this or you not? Nobody's convinced yet?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. I learned one more thing in last 2 sessions. I mean, at least I tried to say that, or at least I tried to explain it to you. Don't draw theoretical stages using graph paper. Instead, we should do tray by tray calculations. Have we learned this?
Yes, sir.
Because the compositions that we might be interested in for actual real life practice, we would be interested in compositions of the order of 0.999 or maybe even 0.9999. Maybe ultra high purity solvent are required in some pharmaceutical formulations. You don't want impurities to go in your stomach or in your eye or in your ear, whatever antibiotics or whatever medicines you take. You may need ultra high pure solvents or reagents and things like that. So for that, you may need a very high purity. And if you are getting that purity by distillation, then you can't afford to draw, you can't afford to use a graph paper, you can't afford to use a pencil, because in that pencil thickness, you have lost several stages. The compositions are not accurately depicted if I use pencil and pen and paper. Do you agree with this? Yes, no?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Anything else anybody has learned? Somebody say something. I mean, what did you learn? It is an open-ended question. It is up to you. What have you learned in 2 sessions? Say something. Somebody say something. I'm just trying to recollect. I'm just trying to make you recollect what we have done in the last 2 sessions. Yes, no. Any more things? Any more things we have learned? Just go back to your notes, last 2 sessions, whatever notes you have taken, whatever calculations you have done. Think, what have you learned? Did you learn anything more? Somebody say something, anything, whatever comes to your mind. This is
So
yes.
thermodynamic correlation gives more accurate results.
Yes, yes. It is not just question of more accuracy, it is more physically realistic. If I use constant alpha, I told you about drawing a smooth curve. So that's what we were talking about, drawing a smooth curve versus using thermodynamic models. Excellent. Is that what you meant? Smooth curve may look better, it may go through all the points. Thermodynamic model may look bad, it may not go through all the points, but it is more realistic, it is able to predict, whereas smooth curve you will not be able to predict it. Remember, for the case that we showed, smooth curve did not show an azeotrope, whereas thermodynamic model showed an azeotrope, and in reality there is an azeotrope for that particular system. It is propanol and water. Is that what you meant?
Yes, sir.
Okay. Okay, anything else? Anything else that we have learned? No, nothing else we have learned.
A and T relation.
Right. So these model parameters depend on temperature because they represent interaction between components, and interaction becomes weaker and weaker as the temperature goes up. Therefore, it typically follows an exponential relationship, like an Arrhenius kind of expression. So they do depend on temperature, and that's how we in fact converted isothermal data into isobaric data. Yes, anything else? Anything else did we learn?
Representing ternary diagram on the right angled triangle
Yes,
rather than
yes,
equilateral.
yes. Representing data. Oops, not just any data, ternary data on triangular diagram. Maybe equilateral, maybe rectangular. That's okay. Um, one more thing we learned related to these triangular diagrams. Do you remember? Yes, no. Somebody say something. Don't you notice something about this triangular diagram? One very important property we talked about.
D, F, and W comes in a straight line.
Right. So the distillate, feed, and bottom compositions are represented by a straight line. They are collinear. What else did we learn? Excellent, Revati. What else did you learn? So I think let us go forward. Perhaps you should all think about it yourself. What have you learned in last 2 sessions, and maybe every lecture, perhaps you can try to summarize what new thing did you learn in that particular lecture. Okay, let's go forward. So let's discuss these two doubts. One one doubt is about the feed plate. So for example, if you have started doing plate by plate calculations and you have started going from this plate, let me just zoom in a little bit. You have started your calculations from this bottom plate and you go to the second plate and then the third plate and then the fourth plate and then the fifth plate and so on, but you don't reach this feed composition. Maybe the composition that you have reached somewhere here is 0.32, 0.7, and maybe 0.08, something like that, right? You don't reach these calculations. So now it is up to us where to switch our feed plate. Should we switch the feed plate where toluene is close to the component, the feed composition, or whether the benzene is close to the feed composition? Do you understand what I'm trying to say?
Yes, sir.
So somewhere as you go from one plate to, as you go from one plate to another to another to another, you might find that on say fifth plate, I'm just taking some number, actual calculation will tell you what number. On some fifth plate, toluene composition is close to 0.3, but benzene composition is not close to 0.3. Whereas on maybe some other plate, you are close to benzene equal to 0.3, but you are not close to toluene equal to 0.3. Does that happen, Siddhant? Is that what you are trying to say?
Yes, sir.
So now the choice is yours as to when to switch over. So what this particular column is doing, it is separating benzene from toluene. Do you agree with that? It's separating benzene from toluene. It is allowing all toluene and xylene to go down. Do you agree with that? So essentially the column is separating benzene and toluene. Do you agree with that, Siddhant?
Yes, sir.
So in terms of some of these notations or nomenclature you would have heard, what is the key component or the key separation? The key separation in this case is benzene versus toluene. The key non-volatile component in the distillate is toluene. The key volatile component in the bottom is benzene. You are essentially doing the benzene versus toluene separation. Do you people agree with that? Yes, no?
Yes, sir.
So we could switch over when in the rectification section, what do we want? We want enrichment in benzene. In the stripping section, what do we want? We want removal or stripping of benzene from the liquid. Do you agree with that? Let me repeat. In the stripping section, what we want is removal of benzene essentially from the liquid. Whereas in the rectification section, we want enrichment of benzene in the vapor. We want toluene to go in the liquid phase. So we might switch over when we have benzene composition similar to the feed plate. We switch over from the stripping section to the rectification section when benzene composition is closer to the feed plate. But there is no reason you can even switch when toluene is close to 0.3. Benzene can be more than 0.3. Yeah, Siddhant.
Yes, sir. In the stripping section, we are considering, we are separating, we are enriching benzene.
No,
But
stripping
sorry, in the
section. Stripping section, we are stripping out benzene from the liquid. That's why it is called a stripping section,
Yes,
isn't it?
Yes, sir.
In the rectification section, we are enriching benzene in the vapor. That's why it is called as rectification section.
So, but from you are saying that we are enriching benzene from toluene.
Correct, because all the xylene you want, essentially no xylene here. So all the xylene is going to go to the bottom of the column, isn't it? Your key separation is between benzene and toluene, not between toluene and xylene. If it was between toluene and xylene, you would have got toluene here and benzene here, both components here.
Sir, but what with benzene and xylene?
Benzene and xylene, so in terms of order of volatility, toluene comes in between, right? So either we are talking about benzene toluene separation or we are talking about toluene xylene separation.
Oops.
Isn't it?
Yes, sir.
So it's not like we are separating benzene from xylene. No? Toluene is there now in between in
Yes,
terms of
yes.
volatility basis. If I wanted this column to separate toluene from xylene, I would have got benzene here as well as toluene here, and I would have got practically nil benzene and practically nil toluene here,
Yes, yes.
isn't it?
Yes.
So the key separation that we are doing is between benzene and toluene. Do you agree with that?
Yes, sir.
So if I want to do a quick calculation, I might even say that I will treat this as a pseudo binary. I will say benzene is 0.3. Maybe I should put some other color. I will say that it's like a pseudo binary. I will say benzene is 0.3, and I will put some component, let's say some W, or no, I shouldn't take W, some third component or a pseudo component which is 0.7, and let this pseudo component have properties of toluene, as if the xylene is not interfering at all in the benzene versus toluene separation. Do you agree with that? But it is dangerous to do this. It is for this benzene, toluene, xylene, we are simply using Raoult's law. Therefore, it is okay to do this. But it is not a good idea to do this because the third component can have a significant impact on the separation. What the third component is. Suppose it is benzene, toluene and water, or benzene, toluene and xylene, or benzene, toluene and ethanol. So what the component is does make a difference. So it is not a good idea in general to treat it as a pseudo binary mixture. But just to give you an idea that what are we separating in this column? We are separating essentially benzene from toluene. Do you agree with that? Yes, no, somebody say something.
Yes, sir.
Are we going too fast? Are we going too slow? Are people sleepy? Are people tired of listening? Want to do some calculations? Nobody is saying anything. That means online
Understood,
hangover.
sir. Understood, sir.
Yes, agree, sir.
Okay. I thought online hangover has happened. So you, in fact, what I would suggest you do is you switched from the rectification line to the stripping line when you are closer to toluene composition, and see how the tray by tray composition looks like. Or you switch over when the benzene composition is near to the feed section, to whatever the tray composition, there you switch over and then you see how it affects. So you do and see for yourself, where should we switch? Choice is yours. All right. Try. Anyway, you're doing calculations in Excel only. You're not doing manual calculations. So there's nothing right, there's nothing wrong. Whatever I say need not be right. Whatever comes by thermodynamic calculations, in this particular case, Raoult's law, and you're doing tray by tray calculations, you are doing material balance as well as you're doing thermodynamic calculations. So whatever I say has no meaning. Whatever calculations, whatever you get by your calculations, that is more important. So don't agree with whatever I'm saying. Don't believe whatever I'm saying. You do for yourself and you see where to switch over. See what difference does it make if you switch over on, let's say, when your toluene composition is close by, when your benzene composition is close by, when your xylene composition is close by. You see for yourself. Does that uh, answer your question, Purvi, Siddhant, Amol?
Yes, sir. A little bit
Yes,
doubt
sir.
more, sir.
Yeah, ask.
So, like in the same question, benzene toluene. So, on the 14th stage, I'm getting 0.31, 3.34, and the next step I'm getting 0.51. So when should I change from stripping section to rectifying section?
How does it matter? You change over here because it is closest. Okay, but it
Yes, sir.
doesn't matter. It will disturb the feed plate, right? So your feed composition need not be what comes by calculations. then in that case your feed plate is definitely going to disturb the column. So it's okay. Right now we are not doing such a great detailed calculation as to account for the disturbance by the feed plate. We are just simply switching over. But if such is the case that here it is, let's say 0.25, some plate 20, some plate 10 it is 0.25, and plate 11 it is 0.4, somewhere in between is your feed. So then on that feed plate we will have to do a proper calculation, a separate calculation for the feed plate. But let's not do that too much in detail, and that's okay. You switch over either here or here. My guess, I mean my suggestion would be switch over when it is closest. Here it has gone still very far.
Okay, sir.
Okay, now your second doubt is when should we, how to calculate diameter. Okay, so we talked about this, where did that go? Here. We talked about this Eckert correlation, isn't it? So now in a distillation column, what do you know? You know the reflux. Suppose reflux is 5. Correspondingly, you will know the liquid flow rate and you will know the vapor flow rate. Say so many kilomoles per hour of liquid is flowing and so many kilomoles per hour of vapor are flowing. Am I correct?
Yes, sir.
Now what is this? Your x-axis is simply a ratio of the liquid flow rate to gas flow rate, isn't it? So column diameter does not appear into this x-axis coordinate. Do you agree with that?
Yes, sir.
So suppose x-axis coordinate comes out to be, let's say 0.1 based on these liquid flow rate and vapor flow rate. So you go from this 0.1, you go all the way to this line. This is your flooding line. Now definitely you don't want flooding line. You want, let's say, some percentage of flooding, some 70-80% of flooding. So if you see these numbers, these are in terms of pressure drop, in terms of Pascal per meter of the packed height. So say I want this line corresponds to 1000 Pascal per meter, 800, 400, 200 and 100. So suppose this flooding line I don't want, I want something lower than flooding. So let's say I want this particular line to be followed for my column operation. Means at this 0.1 the y-axis should be, let's say, 0.1. Now what does y-axis depend on? It depends on the gas velocity, rho g by rho l and mu l raised to 0.1 and packing factor. So once you choose a packing factor, so this gas velocity, now you know the flow rate, you know the gas velocity. So can you not calculate the diameter? Do you agree, Purvi?
Yes, sir. So, but the density is changing with the temperature.
Yeah, sure. So you see where this ratio is high, where this ratio is low. So suppose I calculate this x-axis value, suppose I calculate it near the topmost plate, suppose I calculate it near the bottommost plate. Suppose I calculated these two values. Can you tell me where this value will be high, where this value will be low? Will this value be here, or you calculate here or here? Which value will be near the feed plate, which value will be near the top plate, which value will be near the bottommost plate? At the topmost plate I have lot of liquid because reflux is coming. At the feed plate I have lot of liquid. At the bottommost plate, liquid flow rate is highest. Do you agree with that? Hello?
So I'm not understanding.
Okay, what is this? Have you seen this in your Coulson Richardson books or Trebal book or something like that? This mass flow rate of liquid divided by mass flow rate of gas multiplied by square root of rho g by rho L. Do you agree with that?
Yes, sir.
Now you tell me whether this ratio will be high near the top of the column, near the middle of the column, or near bottom of the column. Where this ratio will be high. At top, I agree with you. It is going to change from top to bottom. So that's what I'm asking. Where the value will be high? Will it be high at the top or feed or bottom? Or even if you want to forget about feed, even if I just want to look at top or bottom, you tell me where this ratio x-axis value, suppose liquid flow rate is some 500 and gas flow rate is some 100, we can calculate from this number. Now the liquid flow rate and gas flow rate are going to depend on the reflux ratio. Do you agree with that?
Yes, sir.
I don't think so. Maybe you are saying yes, but I don't think anybody else is asking anything. They are simply silently observing. Suppose I say this feed is 100 kilomoles per hour and distillate is 50 kilomoles per hour and bottom product is 50 kilomole per hour. Can you tell me what is the liquid flow rate in the column and what is the gas flow rate in the column? Molar flow rates. Can we calculate? Yes or no?
Yes, sir.
You can calculate. Who else can calculate? We talked about this last time. Hello.
Yes, sir.
Yes, sir.
Yes. Yes, sir.
So suppose reflux ratio is 2, then this will be 100, isn't it? And then this 100 gets added up and this vapor would be 150. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Only Purvi is agreeing. I don't want Purvi to agree. So suppose reflux ratio is 4, then this would be 200 and the vapor would be 250. So suppose now at any particular value of R, say reflux ratio is 3, can we calculate the liquid flow rate and can we calculate the vapor flow rate in terms of kilomoles per hour? Do you agree? Will you be able to calculate or not able to calculate?
So we'll be able to calculate.
Yes, sir. We will be able to calculate.
Excellent. And will you be, and last time we have seen that this liquid and vapor flow rate above the feed plate and below the feed plate are different because the feed is superheated. We are taking feed as the saturated liquid. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
So all I'm asking now is if I look at above the feed plate or let's say top of the column, topmost plate, or bottommost plate, you will be able to calculate the liquid flow rate. You will be able to calculate vapor flow rate. Bottommost plate, you will be able to calculate liquid flow rate. You will be able to calculate vapor flow rate. Do you agree?
Yes, sir.
Yes, sir.
Now suppose reflux ratio becomes 6. Now again you will be able to calculate if reflux ratio becomes 8, again you will be able to calculate. Yes or no?
Yes, sir.
So all I'm asking is at a particular reflux ratio, let's say reflux ratio is 5, you have calculated this, you have calculated this, you have calculated this, you have calculated this. Can you not find out this ratio? Can you not find out what the value is on the x-axis?
Yes, sir. We can find out.
Yes. So now I am asking you whether the x-axis value near the top of the plate will be high or near the bottom of the plate would be high.
Near the bottom.
Why is that?
So because the liquid flow rate is greater at near the bottom.
Okay. So if my point, let's say, is somewhere here, this point, let's say, is near bottom of column, and let's say this point is somewhere near top of the plate, near top of the column. Do you agree with that?
Yes, sir.
Now, how to find diameter? So if I have to find diameter near the bottom of the column, if my y-axis value is this, it will be flooding. If at the top of the column, if my y-axis value is this, it will be flooding. Do you agree with that?
Yes, sir.
We don't want it to flood. So the y-axis value should be something lower than this value or this value. Do you agree with that?
Yes, sir.
Yes, sir.
So let's say near the bottom of the column, I want my y-axis value to be, let's take another color now. I want my value to be, let's say, here. So what is the value? Go to here. This value is 0.02. 0.01, 0.02, 0.03. So 0.02. So I want the value of this y prime to be 0.02. What is y prime? That is this number. Or you can calculate it from this number. So x is suppose 1. If x is suppose 1, then ln y would be -4. And then you can calculate y, whatever that value of y comes out to be. So now what is the value of y? Suppose that value of y comes out to be 0.02. So that means you want ug square g epsilon cube a bar rho g by rho l mu l by mu w raised to 0.2. You want this to be 0.02, isn't it? So if you know the packing type, you can calculate the surface area, you can calculate the voidage. G is known, rho g rho l is known, mu l mu w is known, 0.02 is known. So I can calculate ug, gas velocity, superficial gas velocity. Do you agree with that?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So now if you know the molar flow rate and you know the superficial velocity corresponding to this point, can you not calculate the diameter?
Yes, sir. We can calculate.
Only Siddharth can calculate.
Yes, sir. We can calculate.
So now you calculate at the bottom of the column, at the top of the column. Sorry, at top of the column, bottom of the column, bottom and top. Which case the diameter will be larger? Where the y-axis is smaller, isn't it? Hello?
Yes, sir.
Yes, sir.
So that means if I calculate diameter based on the bottom of the column liquid and vapor flow rates, I will get a higher value of the diameter. Whereas if I calculate based on the top of the column, I will get a lower diameter. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
So So use these relationships. This is at flooding. Okay. So actually in refineries, your column diameter is bigger at the bottom, and then there is a feed plate, and your column diameter is lower in the top. It's obviously it's not that different. So wherever big columns are there, you can even have a different diameter at the bottom and at the top. Here the diameter is different because the liquid and vapor flow rates are different. Here the diameters are different because the liquid and vapor flow rates are different. But if the difference is not large, if column diameters are not large, fabrication issues are there in fabricating such columns. So you might want to just fabricate the entire column with a bigger diameter, whichever you calculated from the bottom of the column calculations. Do you agree with that?
Yes, sir.
Sir,
So
when
now,
we are increasing the dia at the bottom, then there is a benefit of mass transfer and benefit of pressure drop. But when we are increasing the dia of the top, then the mass transfer will decrease because velocity is decreasing. So efficiency of column shall be decreasing.
yeah, true. But you do that not for the purpose of efficiency, you do it for the convenience, and you do operational fabrication convenience. Because if you have two different diameters, you have unnecessary thermal stresses in the column, unnecessary mechanical stresses in the column, which may lead to failure of the column.
Yes, sir.
So
Got
it is
it.
more of convenience than from efficiency point of view.
Okay, sir.
But yes, efficiency point of view can be important. That's why in big operations like refinery, where you have huge columns, loss of efficiency would play a part, and therefore you will necessarily fabricate two different diameters in the rectification section and stripping section. Absolutely
Yes,
right.
sir.
Right. So right now we are not looking at all those issues. Right now issue we are looking at is using this formula to calculate diameter for a given reflux ratio. All right. Now if the reflux ratio changes, you can again calculate what will be the liquid flow rate, what will be the vapor flow rate, what will be the diameter. Is that okay? Do you agree with that?
Yes, sir.
Now will you be able to calculate?
Yes, sir.
That's what I have been saying for last two classes. If you get stuck, we can always have a small 1 hour session just to address your difficulties so that your calculations are not held up till the next class. Why not just meet on some day? Shall we fix a date? Shall we meet on Friday as well? Maybe Friday it can be just 1 hour or something like that. Or Saturday. I mean, what is convenient? Rather than waiting for doubts to be answered in the next class, why not we meet sometime midweek, end week? Shall we or shall we not, or what do you want? Say something. Nobody's saying anything. Means we don't want to meet
So midweek.
midweek. So you tell me a date and you tell me time. Accordingly we will meet, or we need not even fix just now. We can keep it flexible that this week we will meet on Thursday, and next week, depending on how many people have doubts, we can meet on some other day. But let us meet so that all difficulties don't make you stuck till the coming week. Okay, shall we go forward?
Yes.
So I told you last time we would be looking at azeotropes, and we'll be looking at distillation of azeotropic mixtures. So let me share some slides. Wait a second. Why it is not sharing? Seems to have a hand. 1 second. All right, let's start talking about. Are you able to see?
Yes, sir.
Yes, sir.
Okay. So let's look at one of these. Let's say we have a system of carbon disulfide and acetone. The vapor liquid equilibrium in terms of T and XY look like this. So X is equal to 0, X is equal to 1. So X is equal to 0. The boiling point is, let's say, 56, 57. X equal to 1. The boiling point is lower, let's say 45, 46. If it had been following Raoult's law, the Txy would have looked something like this. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
But now it is not looking like this. It is looking like this. The Tx line is like this, and the Ty line is this. Right? So this x equal to 1 corresponds to pure CS2, x equal to 0 corresponds to pure acetone. More volatile component is CS2. Do you agree with this?
Yes, sir.
Yes, sir.
Yes, sir.
So now if I want to write this in terms of, or if I want to depict this in terms of y versus x, what do? I take isotherm lines and correspondingly I plot the x versus y curve. That looks something like this on the left side of this point. On the right side of this point, the y is lower than the x. So the curve looks like this. And at this particular point, x and y are identical. X is equal to y. Do you agree with that? This is a basic thermodynamics that you've done already in the last semester.
Yes, sir.
Yes, sir.
Yes, sir.
So this point is called as an azeotrope point. If it is, that means at the azeotropic point, x and y are the same, no more distillation can happen. So in this part of the curve, alpha is greater than 1. In this part of the curve, alpha is less than 1. And at this particular point, alpha is 1. Y and x are the same. Do you agree with that? Yes, no?
Yes,
Yes,
sir.
sir.
Yes, sir.
All right. This azeotropic temperature, the boiling point of this azeotropic mixture is lower than the individual boiling points. So this particular azeotrope is called as a minimum boiling azeotrope. minimum. Temperature of the azeotrope is lower than the individual components. It is the minimum out of the whole, it is the minimum temperature out of this whole range of composition. That's the minimum temperature, lowest temperature. So it is called as a minimum boiling azeotrope. Okay. Look at something else, acetone and chloroform mixture. So again, x equal to 1, this means it is pure acetone. X equal to 0 means it is pure chloroform. Had Raoult's law been applicable, our Txy would have been like this. Let me draw it properly. I mean, you get the point, right? This would have been how Tx and Ty would have looked like had Raoult's law been applicable, right? But it is no longer applicable. The Tx looks like this and the Ty looks like this. Now here in this part, if I want to convert this into an xy curve, in this part below the azeotropic composition, the relative volatility is less than 1, above it is more than 1. X is great, y is greater than x, alpha is greater than 1. In this case, y is less than x, alpha is less than 1. This particular point, x and y are the same, x and y are the same, and alpha is equal to 1. This particular temperature, azeotrope temperature, is higher than the individual boiling points. It is the maximum temperature over this entire temperature range or this entire composition range. So this particular azeotrope is called as a maximum boiling azeotrope. Okay, can we go forward? Everybody happy up to this? Everybody okay up to this? Anybody not okay up to this? Anybody has doubts up to this point?
No, sir.
Okay, sir.
Only 3 people are saying okay. Rest
Yes,
27 are
Okay,
saying,
sir.
Yes,
Okay, sir,
fine.
are
got it.
sleeping.
Okay, sir.
Oh,
Okay, sir.
okay, awake. Okay. Suddenly people have become awake. And they don't know what they are saying okay for, because they hear 20 other okays, they also say okay. Is that why you are saying okay, or it is really okay to go forward? Because now I'm going to ask a question based on this. Yes, no. So suppose this particular value is like, say some value 0.65 or 0.67, something like that. Just take 0.65 for example. And let's say this particular value is 0.3. All right. Can we go forward?
Yes, sir.
Now I take a distillation column. Okay. Assume that in this distillation column we have R very, very large, and number of theoretical plates are also very, very large. Okay, as if it is like infinite reflux, and as if we have infinitely tall column. It's not infinite reflux because some separation is occurring, so we have to take out a product. So R is very large, let's say 20 or 30, and very large number of theoretical plates, let's say 100. Can everybody visualize?
Yes, sir.
Yes, sir.
Now in this feed, let's say I am putting CS2 and acetone mixture, and let's say CS2 and acetone, I have 0.5 CS2 and 0.5 acetone mole fraction. Let me write it properly. This feed mixture is CS2 and acetone. Mole fraction is, let's say, 0.5 and 0.5. Now you tell me what will be at the top of the column and what will be at the bottom of the column product. What will be my distillate and what will be my bottom composition. Everybody is waiting for somebody else to say something.
So I don't think the product formation will be there because at 0.65 it won't, after 0.65 it won't separate.
No, you tell me what will be my distillate and what will be my bottom. If you want to tell me in terms of composition, you can tell me in terms of composition.
So at the top it will be 0.65 of CS2, I think.
Bottom? Purvi, bottom. What will be at the bottom?
So I'm thinking, sir, I don't know.
Okay.
Yes, sir.
Okay. Think. Anybody else? It's not that Purvi has to give all the answers. Just because she's CR doesn't mean she has to give all the answers.
Sir, I think actually after 0.65, since the y-x diagram is below the diagonal, it will not come out as 0.65. It should decrease.
No. You tell me. I don't know whether it should decrease, increase 0.65, 0.8, 0.9, 0.7, 0.3. I don't know. I am only giving you this diagram. I am having a column with a very large number of theoretical plates, 100, 500, 1000, whatever you want. And I am having a very large value of reflux ratio. 20, 30, 40, 50, whatever you want. You tell me what will be the bottom composition and what will be the top composition. Whatever you think.
The bottom can be pure acetone.
Yes, sir.
Nothing else was heard. If you don't like this first question, you can answer the second question. The feed is 0.7 CS2 and 0.3 acetone, or if you don't like 0.7 and 0.3, make it 0.8 and 0.2, whatever is your favorite number. Again, we have infinite reflux or very large reflux, and number of theoretical plates is very large. You tell me, if you don't like the first question, you can solve the second question. Only Purvi and Amol seem to be attempting something. Other 28, or should I take names now at random? Well, of course, we don't have 28. We have only 23.
Sir, in the first case, I think we can have pure stone
Where?
as a bottom.
So you are saying 0 and 1.
Yes, sir.
What about top?
Sir, as the same as Purvi.
So you are agreeing with Purvi, 0.65 and 0.35.
Yes, sir.
That is one answer. Any other answer? We can keep on writing
So
answers here.
in the second case, we will get CS2 in the bottom because driving force is negative.
Second case, that
At
means
x
this
is equal to
0.8,
0.2.
0.2 case. Is that what you are saying?
Yes, sir.
Shubham, second case means which case are you saying? This
Yes, sir.
0.8 and 0.2 case feed?
Second case means where
So
CS2.
top composition?
Yeah, yes, sir. Yes, sir.
Problem 1
I don't know the
and
composition, but
problem 2.
CS2 will
Which
be
problem
at the
number are you
bottom
saying?
because the driving force is negative.
Are which problem number? Problem 1 or problem 2?
I'm talking about problem number 2.
Huh? Problem
Problem
number
2.
2. Okay. Now problem number 2, distillate
Sir,
and
problem
bottom.
2 I'm talking about.
Okay, I have understood you are talking about problem 2. You tell me the compositions.
Sir, CS2 will be in the bottoms because I will.
No, you tell me composition. Na?
That time.
You want 1 and 0? What do you want? You tell me what composition you think you will get. Don't say CS2 will be in bottom. Tell me composition.
Sir, wait, I'm thinking. Yeah, yes, sir. Okay. Yes, sir.
CS2 can be at the top also, bottom also. Acetone can be at top also and bottom also. I don't know. Only 3 people are attempting.
Sir, I think it will be opposite of problem 1.
Hey, are you going to join
Uh,
politics?
no,
No, if
sir,
if you are in party X, if you are in the ruling party, you say, oh, opposition. Whatever opposition says, you say exactly opposite of that. Or if you are in the opposition party, whatever the ruling party says, you say exactly opposite of that.
sir,
ऐसा है क्या?
from top we will
No,
get
no, you
pure acetone.
don't tell me that problem 1 and problem 2 will be exactly opposite. You tell me compositions.
Sir, top will be in problem to top will be pure acetone.
Pure acid. So 1 and 0. Is that what you're saying?
Yes, sir, and bottom will be 0.65 and 0.35.
Okay. We have one answer.
Sir, problem 2, the top one will be pure CS2.
So second is 1 and 0. Bottom?
Others are same. Others are same, sir. 0.65 and 0.35.
Okay. So immediately we should say exactly opposite. No, so 1 and 0. 0.65, 0.35. Exactly opposite. 0.35, 0.65. 0.35, 0.65. कुछ तो बोलो यार, कुछ भी बोलो, कुछ तो बोलो. only 5 people have attempted. Other people are not even attempting. So now I will take names at random. Raghav, what do you say?
Sir, in problem 2, the above composition will be 1 and 0.
Which is 1, which is
Like
0?
which is written already.
No, everything is written. 0 and 1 is written, 1 and 0 is also written.
No, sir, as told by Sharon.
So I don't know who's telling what. You tell me what is your answer.
Sir, in problem 2 at top, CS2 will be 1 and acetone will be 0.
Okay, and bottom?
And sir, bottom, I'm thinking.
Okay. अभी now I have written everything possible, isn't it? अभी इसमें से कुछ तो एक तो होगा. Do you agree that it has to be something out of this?
So the same thing.
Which same thing means which thing? I have written 4 for top, 4 for bottom, 4 for problem 1, 4 for problem 2.
So instead of pure CS2 or acetone, there will be some composition like 90% or 80%.
Okay. Okay, maybe I will ask a different question. Maybe I will ask a question that I have benzene and toluene. I have very large reflux and very large number of theoretical stages. Now you tell me what is the composition of benzene and toluene at the bottom and benzene and toluene at the top. Starting with, let's say, 0.5, 0.5. Now this should be straightforward.
So pure benzene at top and pure toluene at bottom.
How many agree? How many disagree?
Yes, sir, I agree.
So I think not pure, but 0.999, 0.001.
अरे बाबा very large रे बाबा, very large. Very large मतलब तुम how many ever you want उसका double. So suppose you want 100, take 200. Suppose you have 200, take 500. People are not saying
Yes, sir,
anything that cannot happen. Otherwise, we'll stop the lecture. If nobody wants to say anything, we will stop the lecture. Because nobody wants to say anything.
Agree, sir.
Agree, sir.
Agree, sir.
Agree, sir. Agree, sir.
Still, I am not hearing 23 agree. Means somebody is disagreeing.
Agree,
Okay,
sir.
whoever is disagreeing, speak up. Why do you disagree? Nobody is disagreeing. Is everybody else agreeing or disagreeing? Say something.
Agree, sir.
Purvi doesn't want this one. She is not happy with this one. Now you are happy, Purvi?
Yes, sir.
No, but the problem is we don't have an analytical instrument that will measure so many lines, and we don't have an analytical instrument that will measure so many zeros. So what your analytical instrument will measure is 1 and 0. Is that okay?
Yes, sir.
Okay. Why benzene goes to the top of the column and why toluene goes at the bottom of the column?
Benzene is more volatile. So.
Yeah. So I think connection went. Now, are you able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, now let's see. Do you people agree that whichever component is more volatile will go to the top of the column and whichever component is less volatile will go to the bottom of the column? Do you agree with that?
Yes, sir.
So if I
Yes,
have
sir.
Yes, sir.
Yes, sir.
Sir.
okay, now excellent. Now you seem to be talking. Now you tell me that in this particular case, which is more volatile? CS2, acetone, or the azeotrope?
Sir, below 0.65 CS2 is more volatile and above 0.65 acetone is more volatile.
Let me repeat the question. Let's not be in a hurry to answer.
So azeotrope.
I am asking
Azeotrope
out of
is
the
Azeotrope.
I am saying out of these three components, CS2 is one component, acetone is one component, and if azeotrope is one component, a mixture really, it's a constant boiling mixture, means X and Y are the same. Which is more volatile, CS2 or acetone or azeotrope?
Azeotrope.
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 On what basis are you saying azeotrope is more volatile?
So
It
lower
has less
temperature.
boiling.
Lower
Less
Lower boiling
boiling.
temperature.
Correct. Pressure is equal to constant. So pressure is equal to suppose 1 atmosphere. Then acetone will boil at 56. Pure CS2 will boil at something like 46. But the azeotrope will boil at something like 39. So whichever one is having a boiling point less at a constant pressure means it will be more volatile. Do you agree with that?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now look at problem number 1. My composition is here 0.5. So that means we are on the left side of this azeotrope. On the left side of azeotrope, tell me which is more volatile? Hello?
So azeotrope is more volatile.
Azeotrope is more volatile. What is less volatile?
Acetone.
On the left side of the azeotrope.
Acetone.
Left side of the azeotrope, acetone. This is acetone, isn't it? Do you agree? Disagree? Yes, no, somebody say something.
Yes, sir.
Yes, sir. Agree.
So now you tell me compositions. Now tell me what will be there at the top, what will be there at the bottom. Top, more volatile. What is more volatile? Azeotrope. What is the azeotropic composition?
0.65, 0.34.
At the bottom, less volatile.
0.1.
0.1.
So, which means if I am having 0.5 as a feed, look at the X versus Y. This is my feed. The distillate can be at the most the azeotrope point, and the bottom product can be at the most 0 CS2, which means pure acetone. Do you agree with that? We'll have
Yes,
to,
sir.
even if I have infinite stages, I will have to do triangles and infinite reflux. Topmost composition would be azeotrope, bottommost composition would be pure acetone. Do you people agree? Do you people disagree? Is everybody okay? Everybody okay with this?
Yes, sir.
Yes, sir.
Now let's go to problem 2. Our composition is CS2 0.8 and acetone 0.2. That means we are somewhere here. Sorry, 0.8, no? 0.8 is here. We are on the right side of azeotrope. That means our feed is here. This is our feed. Now on the right side of the azeotrope, what is more volatile?
CS2.
And
no,
azeotrope is still more volatile. It has lower temperature than CS2, isn't it?
Azeotrope.
Yes, sir.
So at the top, I will still have 0.65 and 0.35, but bottom would be now pure CS2. It will be 1 and 0. Do you agree with that?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
Now, who was saying exactly opposite? Problem 2 is exactly opposite of problem 1?
Sir, me.
The politician amongst you. So Vaibhav, do you see? Is it exactly opposite? No.
No, sir.
Yeah, I'm just joking, huh? When I say politician, it's just a joke. Just take it as a joke. Don't take it seriously. Vaibhav.
Yes, sir. Yes, sir.
The most volatile is the azeotrope out of these three. Therefore, it is called as a minimum boiling. Minimum boiling means temperature is lowest, so volatility is highest out of these three. Do you agree with that? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Now, let's take the other situation.
So I have a doubt.
Yes, please ask.
So I'm not able to understand how we are getting pure acetone in the problem 1 and pure CS2 in problem 2 in the bottom product.
In the first problem, so we had CS2 and acetone here. So this was our feed point. Do you agree with that? 0.5. Yes or no?
So can you please repeat?
What is our feed composition? 0.5, 0.5.
Yes, sir.
Where is that feed point? Here.
Yes.
If this is my feed point and I have very large reflux and I have very large column, will I not get the azeotrope at the top and will I not get the pure acetone at the bottom? Very large column.
Okay. ठीक है. Yes, sir.
I wrote Re Baba. Very large R and very large number of theoretical stages. Okay, you may not agree to 0 and 1. Do you agree to point?
No, sir, I got it.
No, wait Re Baba. Some people have problem with 0 and 1. I agree. 0 and 1 is impossible. It will be 0.999999999. So many nines you can say and so many zeros you can say. Now are you happy?
Yes, sir.
So that's what I had written. I have no analytical instrument that can measure so many 0.000000001. It will register as 0 and 1. Now, do you agree?
Yes, sir.
All right. Can we go forward?
Yes, sir.
Now, if you have understood, now it should be very straightforward. The second problem should be very straightforward. The second problem is acetone and chloroform. And I will change this also. Acetone and chloroform. Now tell me. Now it should be straightforward.
So at the top, it would be 1, 0.
Which problem? Problem 1 or problem 2?
Problem 1.
Problem 1. Problem 1, it would be
1, 0, 0.3 and 0.7.
Problem 2.
So 0, 1, 0.3.
Anybody else gets any other answer? Anybody else thinks anything else? Point 5, that means I'm here for problem number 1. Or in terms of XY diagram, I'm here. This is my feed. If this is my feed, if I draw triangle, at the topmost point, distillate, I will go to pure acetone and 0 chloroform. And at the bottom of the distillation column, I will go up to the azeotrope point, which means 0.3 and 0.7. Or if you look at the right side of the azeotrope, the more volatile component is acetone, the less volatile component is the azeotrope. Now, if for problem 2, 0.2 and 0.8, we are somewhere here. This is our feed. The more volatile component is now the chloroform. So I will get 0 and 1. And the less volatile component is the azeotrope. Means I will get 0.3 and 0.7. Do you agree with that? Yes, no?
Yes, I agree.
Agreed.
Yes, sir.
Yes, sir.
Sir.
All right. Should we go forward?
Yes, sir.
Should we go forward?
Yes, sir.
Yes, sir.
Now draw PXY curve for all these two systems. So if I have to draw PXY at constant temperature, so temperature is constant, PXY, can you draw? This was pressure was constant. It was TXY. Now PXY would be, how will it look like? If it was an normal non-ideal mixture, if it was a sorry, if it was ideal, like Raoult's law, how would it have looked like? It would have looked like this. This would be Px, this would be Py. Now how will it look like? Azeotrope is at 0.65, let's say. For acetone and chloroform, and for for CS2 and acetone, I should say. This is for CS2 and acetone, this case. And acetone and chloroform we will draw here. Point 3. How will it look like? How will the PXY look like for CS2 and acetone?
So it will
Azeotrope is 0.65 now.
Pressure will be maximum at 0.6.
Pressure would be
maximum
at
0.65.
0.65, correct. So it may look something like this. Isn't it?
Yes, sir.
Yes, sir.
Pressure is maximum, means at a particular temperature volatility is maximum, and x equal to 0 means acetone, so pressure would be lower. X equal to 1 means pure CS2. This is pure CS2, this is pure acetone. Isn't it? Do you agree? For the acetone chloroform system now,
so pressure will be minimum
at 0.2.
correct. Something like this. Okay. Should we go forward? Should we go forward?
Yes, sir.
Yes, sir.
Yes, yes.
Yes, sir.
Now, or you want a break of 5 minutes?
Yes, sir.
Yes, sir.
I think you are in a mood to say yes to everything. So shall we continue up to 9 o'clock in the night?
No, sir.
Okay. I thought people are simply saying yes, sir. Yes. Okay. A break for 5 minutes? 10 minutes? 10 minutes? Break for 10 minutes.
Okay, sir.
We will meet at
Okay, sir.
3:10. All right, shall we begin?
Yes, sir.
Great. So we talked about minimum boiling and maximum boiling azeotropes. So many of the mixtures fall under the minimum boiling azeotrope category. So for example, ethanol water is a minimum boiling azeotrope mixture. Benzene water, toluene water, xylene water, nitric acid water, they all are examples, or ethanol benzene, they are all examples of minimum boiling azeotrope. Now suppose I want to separate this CS2 and acetone mixture. Let's say we have composition 0.5 or 0.4. So let's say we have a feed mixture of CS2 and acetone, mole fraction, let's say 0.4 and 0.6. I want to do something to this mixture, maybe 1, 2, 3, 4, 5, 20 distillation columns, whatever we want to do. What should we do to separate them into pure acetone, pure CS2 and acetone? Can you think about what can be done? Can somebody tell me what to do if I have to separate them into pure CS2 and pure acetone?
Remove the azeotrope.
And what will you do with the azeotrope? If I remove the azeotrope, I will only get either pure CS2 or pure acetone, isn't it? So if I use one distillation column, I will have CS2 acetone and I will have CS2 acetone. This would be 0.65, 0.35. And this would be 0, 1. Isn't it? Have I got pure CS2?
No, sir.
No. So how do I get pure CS2? How do I get pure CS2 now? I got pure acetone. But have I got pure CS2? I want to do something so that I get pure CS2. Pure means almost pure, 0.999999999 if you want, and pure acetone. Can you think?
By changing the process conditions.
Now tell me what condition to change.
Maybe by
Tell me what
using
to do.
pressure swing absorption column, so that pressure can be altered. So we
Pressure
can get
swing
the
absorption.
pressure swing column.
Pressure swing absorption. Absorption. There's no gas, no? They're all liquids. Hello?
Yes, sir. Pressure swing column.
Pressure swing column. What
Yes,
column? What operation? Column is a physical process, physical separation process. Is column a separation process?
I think.
Is column a separation process?
No. No.
Tell me name of a separation process. Or if you want to do distillation, fine. What will I do to this to get me pure CS2?
So we can change the temperature, or we can add some other solvent
No,
with
don't
the.
add any other solvent yet. I don't want to add any other solvent yet. Change temperature. Temperature is different, no? Temperature is different here, 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 here. Everywhere temperature is different. Pressure is constant, 1 atmosphere. Temperature is different, no? Everywhere temperature is different. Do you agree? Temperature changing from 39 to 56. So change temperature means what? Temperature is changing anyway across the column. So you have to be more precise than saying random things. This is not an exam where you will write something and you will get some marks. That is undergraduate job. Write something and examiner will give some marks and we will somehow pass.
We will remove the
So we can
azeotropic
decrease the
point.
pressure.
Shubham, say that again. And after that, Amardeep, you can say. Shubham, what are you saying?
We can decrease the pressure to remove the azeotropic point.
How do you decrease the pressure and how will the azeotropic point be removed, or how will the composition change, or what do you want to do?
So we can go for vacuum distillation.
But how will the azeotrope change? So you want vacuum distillation here itself?
So
or another column?
yes, sir.
Yes, for what? Same column or another
So we
column?
can go for back
I think
another column.
Amardeep, what were you trying to say?
So I was saying the same thing, that remove azeotropic point.
Remove azeotropic point. Now means tell me what to do. Remove azeotropic point. Means what?
By decreasing pressure in the column.
So I want another column. Is that what you're saying?
No, sir, not another column. In the same column, we can decrease the pressure.
Same column, decrease the pressure. What? So you're doing batch-wise operation? So you operate the column, then you change the pressure? Or what are you doing? And nobody wants to add pure CS2 here. So that we go to the other side of the azeotrope. We were on the left side of the azeotrope, right? You look at problem 1 and problem 2 again. We were on the left side of the azeotrope. Now if you go to the right side of the azeotrope, nobody wants to do that. Add pure CS2 to go from left of the azeotrope to the right of the azeotrope. Somebody say something.
So then again, azeotrope will form in the next column.
Okay, so, but if azeotrope forms in the next column, now in the next column, at the top I will have azeotrope, but bottom I will have CS2, no?
Oh yeah.
Isn't it? Nobody wants to do this? Problem 1 and problem 2. Hello?
Yes, sir.
The only question is, where will I get pure CS2 from? Well, then our chemical engineering comes to our rescue. Can we not recycle this? Partly recycle and partly take it out. And this azeotrope can also be recycled. Anyway, it's azeotrope only. Good idea, bad idea?
good idea.
Only one person is listening. All others are listening to music or playing computer games. Do you think it is a good idea or do you think it's a bad idea?
But still, we are not getting any additional amount of acetone.
Acetone or CS2?
Acetone, sir.
Acetone is already come here. Acetone has already come at the bottom of the first column, isn't it?
Yes, sir.
But you're right. So are you saying good idea or bad idea? Acetone has come here as pure. So are you saying good idea or bad idea?
Good idea, sir.
Now you're saying good idea. Earlier you were saying no, we are not getting an extra acetone anywhere.
So if you are able to get additional acetone separated from that azeotrope.
No, you tell me whether this is a good idea or a bad idea. This was the problem 1. And this is problem 2. How many people say this is a good idea? How many people say this is a bad idea?
Sir, this will require large amount of trace and reflux ratio.
No,
so
we
I
have
think
infinite reflux and infinite trace. Whether it is a good idea or bad idea.
yes, sir, that can be a good idea.
Sir.
So let me draw, and then so that everybody knows what I'm talking about. So we have CS2 acetone. This is 0 and 1. This is like our first problem. Now we have CS2 and acetone. We have 0.65, 0.35. This is our problem number 1. So what we will do is we will send it to another distillation column, but I will add extra CS2 here so that the composition after adding CS2 this composition becomes 0.8, 0.2. Now it is like problem number 2. Then I will get azeotrope CS2 acetone 0.65, 0.35, but I will get CS2 acetone 1 and 0.
Sir?
And this wait, and this azeotrope can also be recycled back here, and this CS2 partly is to be recycled and partly to be taken out. So if I take this as a control volume, overall I have CS2 acetone 0.4, 0.6. I have pure acetone CS201. I have CS2 acetone 10. Do you think this is a good idea or a bad idea?
It's a bad idea.
Good idea, sir.
Oh, who's saying bad idea?
So I
Siddhant,
think
you're saying bad idea, huh? And Sharon, you're switching sides like a chameleon. You're changing colors.
No, sir, we are getting pure acetone and CS2, so we are able to.
You started with a good idea, then you said bad idea. Now again you are saying good idea, and now again you are saying bad idea. Nay, what are you saying?
Good idea, sir. Fixed.
You're saying good idea. Okay. Siddhant, what are you saying?
So I think it's a bad idea, sir. Don't we just adding a step and didn't get going anywhere, because we are just adding pure CS2, and in the end we are just getting that thing back, and we still have the azeotrope. मतलब
Azeotrope recycle किया ना हम लोग ने.
सर बट क्वांटिटी तो उतनी है, रिसाइकल तो हम पहले भी कर रहे थे. मतलब आउटपुट तो सर उतना ही आ रहा है, हम जितना CS2 ऐड कर रहे हैं लास्ट में उतना ही CS2 अगर हमें मिल जा रहा है, तो हमें कोई नेट CS2 का तो ऐड मिल नहीं रहा है.
Because whatever we have added, only that much extra we will get here. We will not be able to get any product out. If you do material balance, you do and you see for yourself that it is a terrible idea. Siddhant, whatever you are saying is absolutely right. Material balance, whatever extra CS2 you add to change the composition, only that much CS2 you will get out. Which means again you will have to recycle the whole thing. There will be no product coming out. Is that what you are trying to say, Siddhant?
Yes, sir.
Do people agree with Siddhant or do people disagree with Siddhant?
Yes, sir, agreed.
Only one person agrees with Siddhant, that is Arshit. Siddhant, you have only one friend in the class.
Agreed, sir.
Now, Siddhant, you have two friends. All other people hate you. No, I'm just joking. They don't hate you. Only 3 people say that this is a terrible idea. Rest 17 say, is it a good idea, bad idea? No, not 17. How many? Rest 21. Raghav, what do you say?
Bad idea, sir.
Bad idea. Why is that? Do you agree with Siddhant?
Sir, yes, sir.
Okay. Nitin, what do you say?
So it's a bad idea because some amount of CO2 is always recycled, so we cannot get that much product. So
that much or zero?
Can say because partly amount of CO2 is getting recycled. So
no,
we
but
can
partly it is recycled. The exact amount that we are recycling, only that much we will be able to get. That's what Siddhant is saying. So we'll have to keep on recycling everything.
Yes, then surely it will be a bad idea.
Namrata, what do you say? Revati, what do you say?
So it's a bad idea for the same reasons.
Okay. Amol. Amol is very quiet today.
Yes, a bad idea. No, sir, I'm not feeling well actually from last 2 days. Yeah.
Oh, okay. Okay, so it's a bad idea because if you want to do, you do material balance and see for yourself. Suppose I add 0.1 moles here, take some basis, say I have 100 moles. So you find out how many moles will come here, how many moles will come here. And let's say you add 10 moles of pure CS2 and you find out how many moles you will get. You will get back exactly 10 moles. Then you will have to recycle everything. So don't trust Siddhant. Don't trust anybody. Put actual numbers and see for yourself that this is not a possible way of separating azeotropes. So we are now going to look at different ways of separating azeotropes. One of the ways that we look at, one of the ways that we separate azeotropes is without adding any third component. We'll see that after some time. This is possible only if the azeotrope composition changes significantly with pressure. So this pressure is 1 atmosphere and this Txy data is at a pressure of 10 atmospheres. So this is your Txy data at 1 atmosphere, and this is your Txy data at 10 atmospheres. This is now acetone and methanol. At 1 atmosphere, there is a minimum boiling azeotrope somewhere here. It has a composition of 77.6 mole percent acetone. At 10 atmosphere, the azeotrope composition is 37.5 mole percent acetone. Now, can you propose a distillation strategy to separate acetone and methanol for a feed containing 50 mole percent acetone to separate into pure acetone and pure methanol, taking advantage of this change of pressure? The azeotropic composition changes very dramatically with pressure. Can you draw a column, a sequence of columns, and separate them into pure acetone and pure methanol, starting with a feed containing 50 mole percent acetone? Have you understood the question? Have you understood what I'm asking?
Yes, sir.
Yes, sir.
Yes, sir.
Can you draw? I'll give you 2-3 minutes to draw, 5 minutes to draw. Anybody would like to tell how to draw, how to do?
So
Any volunteers?
first column operating at 1 atm.
Yeah, okay. So we will have first column operating at 1 atm. Okay.
At the bottom, we get methanol.
Wait. I have acetone and methanol. Let's say I have 0.5 and 0.5. Now, top of the column, acetone, methanol. Bottom of the column, acetone, methanol. Okay. So you are saying 0 and 1 here. Okay.
Yes, and top would be the azeotrope.
So maybe let's say 0.776 and 0.4224. Okay, now
next column at 10 atm pressure.
Okay, send this to column at 10 atm.
Top we get the azeotrope of 37.5 more percent acetone.
Okay. Bottom.
Sir, in the top it will be 0.375 acetone and
No, I don't know. I'm only writing whatever you people are saying. 0.776 or 0.375?
0.375.
Okay, 0.375. I'm only writing. I'm not saying yes or no. And this will be 0.625. Sorry, not 625. 538. 38. So 240. Yeah, 625. And bottom?
10.
10. Now what do you do with this azeotrope?
Sir, we can recycle that second column distillate to the feed of the first column.
You want to recycle here. So if you have a plant operating at steady state, do people agree with this? Do people disagree with this? So we have got a pure acetone stream, we have got a pure methanol stream, and rest everything is inside this black box. 2 distillation columns operating at 2 different pressures. Do people agree? Do people disagree? Anybody has any other thoughts? Who was telling Sharon? You were telling? Who was saying all these things?
Sharon.
Yeah, okay, good. Who else? Anybody agrees with Sharon? Doesn't agree with Sharon?
Agreed.
Prajwal agrees. Who else?
I agree, sir.
Niruddha agrees.
Agree, sir.
Siddhant agrees. Now, everybody
Agreed,
agrees.
sir.
Okay. So what we are trying to do, if you think about what you are trying to do, in the first column, you are at 1 atmospheric pressure. So your feed is, let's say 0.5, somewhere here. So now the more volatile component in the first column is the azeotrope. So that is going to come at the top of the column. At the bottom of the column, if I have enough number of stages, and if I have enough number of amount of reflux and enough number of stages, I'm going to get X equal to 0, means acetone mole fraction is going to be 0. I will have almost pure methanol. Almost pure, otherwise some people will shout 0.99999999999 methanol, almost pure methanol. Now we are at the distillate, we are at a composition of 0.77, that is somewhere here. This is our distillate from the first column. If we use that as a feed to the second column, we would be here. Now this is our feed to the first column. Feed to the second column. So now if I operate this second column at a higher pressure, now we are on the other side of the azeotrope. In the first column, we were on the left side of the azeotrope. In the second column, now the azeotrope point has shifted. Now we have come to the other side, right side of the azeotrope. Now the second column, if we operate, our top composition will be the more volatile, which is the azeotrope in this particular case, but it is the azeotrope corresponding to 10 atmospheres. And bottom of the column would be pure acetone. Pure in the sense 0.99999999999. You can keep on saying 99 till you get tired. Do you agree with this? Do you disagree with this? Yes, no? Anybody?
Sir, I have a doubt, sir.
Yes, yes.
Sir, why can't we use the 10 atmosphere column first and then the 1 atmosphere column second?
Fine, absolutely okay. We can use the 10 atmosphere column first as well. There's no harm in doing that. Let's do that. Oops, sorry. Let's do that 10 atmosphere first. So we take a column. This first column operates at 10 atmosphere. We are having 0.5, 0.5 acetone and methanol. We are here. Now top of the column will be acetone and methanol 0.375, 0.625. Bottom of the column will be 1 and 0. Is that okay?
Yes, sir.
Now if you take this as a feed, the distillate from the first column, now we are at 0.375. That means somewhere here. Now this is our feed to the second column. We operate this column at 1 atmosphere. Now if you take this as a feed, distillate will be the azeotrope, acetone and methanol 0.776, 0.224, and bottom would be acetone and methanol, acetone 0, methanol 1. And this acetone and methanol we can recycle back. Absolutely okay. We can have the 10 atmosphere first and 1 atmosphere as a second column. Absolutely okay. So whether to have 1 atmosphere first followed by 10 atmosphere, or whether to have 10 atmosphere followed by 1 atmosphere, that decision will be based on economics. But in general, which one do you think will be first, 10 atmosphere or 1 atmosphere?
10 atmosphere, sir.
10 atmosphere. Why is that?
Sir, फॉरवर्ड फीडिंग की मतलब सर डिक्रीजिंग प्रेशर ऑप्टिमम होता है.
कौन बोला?
सर फॉरवर्ड फीडिंग
कहाँ से आया तुमको ये सब स्टेटमेंट? कहाँ से मगअप किया तुमने?
सर
फॉरवर्ड फीडिंग ये तुमने इवेपोरेटर, मल्टीपल इफेक्ट इवेपोरेटर में ये सब मगअप किया है. फॉरवर्ड फीडिंग, रिवर्स फीडिंग, प्रेशर रिड्यूसिंग विद रिस्पेक्ट टू द नंबर ऑफ इफेक्ट, बराबर ना?
यस सर.
हाँ, तो ये तो इवेपोरेशन है,
तो
डिस्टिलेशन है.
इकोनॉमिक्स के लिए ऑप्टिमम होता था.
कौन बोला?
सर बुक में रखा था.
नहीं, तुम्हारा प्रॉब्लम है कि यू आर ट्राइंग टू मग अप एंड यू आर ट्राइंग टू रिमेंबर rather than using logic and common sense.
Sir, decreasing
the number of plates would be lower if we use the 1 atm first.
Whether we should have 10 atmosphere first or whether we should have 1 atmosphere first.
Sir, 1 atmosphere first.
Why is that?
Sir, second column have less feed, less amount of feed, so that's why.
That's why what? So what?
Sir,
Less amount of feed. So what?
uh, so maintaining high pressure will be less energy taking in second column.
ये सब कहाँ से स्टेटमेंट आता है तुम्हारा दिमाग में? सब कुछ साइंटिफिक जस्टिफिकेशन है? वैभव, साइंटिफिकली जस्टिफाई करो ना, ऐसा स्टेटमेंट मत बोलो, जस्टिफाई करो ना व्हाट यू आर सेइंग. Less amount of feed in the second column, I understand. Now so what? Hello Vaibhav?
Yes sir, yes sir.
So what? Less amount of feed, you have explained. Yes. So do people agree that if I have 10 atmospheric column first followed by 1 atmospheric column, I will have more amount of feed going to the 10 atmospheric column as compared to this. In this case, the 10 atmospheric, so case 1 if I say, and case 2, in case 2 I have more of feed going to 10 atmospheric column, whereas in case 1 I have less feed going to 10 atmospheric column. Do people agree with that statement? That's what statement Vaibhav is trying to make. Am I correct,
sir.
Vaibhav?
Yes,
Is that
sir.
what you're trying to say?
Yes, yes.
No, so what? After that, you made so many statements. Say those statements again. People have not understood what you're trying to say. So, you made 2-3 statements, Vaibhav. Make those 2-3 statements again.
So sir, will require a smaller column, so maintaining 10 atmospheric pressure will require less energy, I think.
Now, smaller means what? Smaller in diameter or smaller in height?
Diameter, sir.
Smaller in diameter, right? So if you see, do people agree with that or disagree with that?
Sir, I think case 1 is better than case 2.
Why is that?
So because in case 2, when we observe the isotropic composition going to 10 atmospheric pressure, the acetone composition is more. So when we have 10 atmospheric pressure, we need there is a more load on the reboiler for the separation.
Correct. So that's what Vaibhav is saying, right?
Yes, so I
load on the
prefer
reboiler is one part, but the diameter also, the amount of heat duty. So what I'm trying to say is that if you send it to the first 1 atmospheric column first, the amount of feed going to the second column, the 10 atmosphere column, is less as compared to the amount of feed going to the 10 atmosphere column in the second case. If that is the case, then your reboiler duty is also less, your column diameter also is less, and because now I have a higher pressure, the cost of the column, you remember, cost of the column will depend on pressure and diameter, thickness of the column. You've studied formulae like this, right? T is equal to P D something something. No, not studied like this. Something F was there and something else was there. You remember some people had eta also, and ये सब
Yes,
मगब
sir.
किया है नहीं किया है?
Yes, sir.
ये क्या है सब? ये P D F eta क्या है सब ये? P is what? D is what? F is what? Eta is what? ये सब मगब नहीं किया तुम लोग ने? नहीं किया? इक्विपमेंट डिजाइन ऐसा कोर्स नहीं था तुमको अंडर ग्रेजुएट में?
Yes, sir.
Yes,
हाँ
sir.
ना? So pressure and diameter, thickness, permissible stress, weld efficiency or joint efficiency, ऐसे सब मगब नहीं किया तुम लोग ने?
हाँ, sir.
हाँ.
Yes, sir.
So if
Yes, sir.
pressure is higher and diameter is higher, thickness would be larger. So in this case, if diameter is smaller, in this case diameter is larger, thickness of the 10 atmosphere column would be larger in case 2 as compared to case 1. So cost would be higher, plus the reboiler, everything would be higher for case 2 as compared to case 1. Do you agree?
Yes, sir.
But don't, only problem is the reflux ratio can be different in the two columns in case 1 and case 2. So it's a question of optimization, but in general this would be better than this. Anirudh, do you agree?
Yes, sir.
Can we go forward? Any other doubt, any other question, any other point? Hello? Any other question, any other point, any other doubt? Anybody wants to say anything? Anybody has an opinion that they would like to express? No, nobody has an opinion. Can we go forward?
Yes, sir.
Yes, sir.
So
Yes, sir.
another example of the same category is THF and water. So at 1 atmosphere, the TXY curve for THF and water is like this. The azeotrope is a minimum boiling azeotrope, 82.3 mole %, whereas at a pressure of almost 8 bar, 8 atmosphere, it's 114.7, but don't worry, it is too small to be seen. So let's say 7.5 atmosphere, 114.7 psi, so just 7.5 atmosphere. The azeotrope is 63.9 mole % THF. So here also we can do the same thing. So suppose I have a feed like this 0.5, or feed is somewhere here 10 mole % THF. That means 10 mole % THF means we are here. If this is my feed, I can do pressure swing distillation, pressure swing azeotropic distillation. I can have two columns, one operating at 1 atmosphere, at the top I will get the azeotrope, so THF and water 0.1 and 0.9, THF and water, 1 atmospheric column will get 0.823 and 0.773, so 1773. Right? Now this goes, and the bottom THF and water 0 and 1, it goes to 0. That means this left side of the azeotropic composition. Now we take the distillate, we send it to second column operating at higher pressure. Now we are at this 0.823. Now the feed is here. Now this is the feed to the second column. So again we will get the azeotrope of THF and water, but now the azeotropic composition will be 0.639 and 0.164, so 361, and THF and water 1 and 0. And this azeotrope we can recycle. Do you agree? Yes, no? Any doubts? Can we go forward? Anybody around? Anybody awake?
No doubt, sir.
Only Purvi is awake.
No doubt, sir.
अच्छा अच्छा
No doubt.
No doubt, sir.
Okay. I thought पूर्वी को responsibility दिया है कि yes बोलने का, so that other people can sleep. सीआर को ये भी जॉब करना पड़ता है पूर्वी. Okay, here is another system: water and butanol. Water and 1 butanol. Now difference here is this acetone and methanol. They were completely miscible. Hello. Acetone and methanol. They were completely miscible in all proportions. So they formed a homogeneous liquid phase always. Always in the sense at all compositions. Single liquid phase. Homogeneous means they formed a single liquid phase at all compositions. Same way here also, THF and water completely miscible with each other in all proportions. That means they formed a single phase, single liquid phase at all compositions. But if you take water and butanol, they are not completely miscible at all compositions. Not completely miscible with each other at all compositions. They are not. Under certain compositions, they form 2 liquid phases. One is aqueous rich phase, means water rich phase, and one is the butanol rich phase. We will call this as an aqueous phase. And we will call this as an organic phase. So if you look at data at 1 atmosphere and we plot mole fraction of the more volatile component, water, this is the boiling point of pure butanol. So this is pure butanol. And this is pure water. So this is 373 Kelvin, 100 degrees centigrade. This is 390, so something like 120 degrees centigrade. It's 100 degrees centigrade. It's 119 or 118 actually. 118 degrees centigrade. Now you see this. This is an azeotrope. Is it a minimum boiling azeotrope or a maximum boiling azeotrope?
Minimum boiling.
Minimum boiling azeotrope. What is the azeotropic composition? Something like this, maybe 0.75. 0.6, 0.7 would be here. 0.75, 0.76 of water. What is the azeotropic temperature? Somewhere here. Maybe 366 degrees centigrade. So 366 degrees centigrade is like 94 or 93 degrees centigrade. Do you agree? Yes, no?
Yes, sir.
Yes, sir.
Now
Yes, sir.
you see this horizontal line. That means if my composition is anywhere between this composition and this composition, it splits into two phases. The organic phase would have this composition and the aqueous phase would have this composition. So aqueous phase would have 98% butanol, 98% water, maybe 2%. So this maybe let's call this as 0.98 and let's call this as 0.42. Okay, this point. Do you agree with that? So this is a question. This is a equilibrium of vapor, liquid, liquid. One liquid is the aqueous phase and the other liquid is the organic phase. VLL equilibrium. Whereas this was only VL, vapor liquid equilibrium. I had liquid phase was only one liquid phase at all times, at all compositions. Whereas now I have two liquid phases. One aqueous rich phase or the aqueous phase, water rich phase has 98% water, maybe 2% butanol. And the other organic phase, butanol rich phase, has 42% water, 58% butanol. Do you agree with that? Anywhere in between, if the composition is anywhere in between these two extremes, it will split into two phases, aqueous phase and organic phase. If composition is anywhere here, it will be a homogeneous single liquid phase. If composition is anywhere above this, it will be single liquid phase. If composition is anywhere between these two, it will split into two liquid phases. Is everybody able to visualize this? VLLE, vapor liquid liquid equilibrium. Have you done this in your thermo course? Say something. Have you done it in thermo course? Do you remember you had a thermo course in semester 1? I think I must have got disconnected. I am only talking to myself. Do you people remember you had a thermo course in semester 1?
Yes, sir.
Ah, you remember. Excellent. Amardeep remembers. Have you done this vapor liquid liquid equilibrium in thermo course? Amardeep, have you done it in your thermo course or you have not done in the thermo course?
No, sir.
No, fine. Okay. Doesn't matter that you are not done. Obviously, you can't cover everything in one course. But do you agree that anywhere the composition, if it was completely miscible, see, if water and butanol were completely miscible and they were forming a minimum boiling azeotrope, it would have looked like this. Do you agree with that? Hello?
Yes, sir.
If they were miscible at all proportions, it would have looked like this. Yes or no? Like this. Like this. Like
Yes, sir.
this. Or like this. Or like this. But they are immiscible with each other between mole fractions of 0.42 and 0.98. So they look like the composition looks like not like this. It doesn't look like this. Rather, it looks like this black. Because anywhere it splits into two phases. Anywhere in between the composition is, it splits into two phases. So the bottom portion of this red curve, it doesn't look like this bottom portion of the red curve. It looks like this black curve. Do you agree with that? Do you disagree? Agree? Somebody say something.
Yes, sir, I agree.
Agree, sir.
Yes, sir.
I agree, sir.
Because it is splitting into two phases. So if it is splitting into two phases, depending on the composition, only the relative amounts of the two phases would be different. If composition is here, I will have more of the butanol phase, less of the water phase. If I have composition like this, I will have more of the water phase, less of the butanol phase. But the compositions would be 0.98 and 0.42. And because compositions are the same, 0.48 and 0.42 and 0.98, the vapor which is in equilibrium will always be the same, corresponding to this minimum boiling azeotrope. Only the relative amount of liquid 1 and liquid 2 aqueous and organic phases would change. Homework. Study VLL equilibrium from Sandler's book. Did you use Sandler's book for the thermo course?
No, sir.
Then which book did you use?
Sir, James Smith.
Bhagwat sir told you to use James Smith, or Bhagwat sir told you to use Sandler?
Sir, he didn't tell us to read from any book.
ऐसा थोड़ी होता है. Standard textbook for Bhagwat sir's course is Sandler's book. Anyway, that's not that important. You do that whenever you get time, or better to do before next class. But do you agree with this? At least, do you agree that the vapor liquid equilibrium for immiscible mixtures would look something like this? Do you agree with that? If you
Yes,
agree,
sir.
then we can go forward.
Yes, sir.
Yes, sir.
Now, suppose I have a 50-50 mixture, or let's say I have a 20-80 mixture of water and butanol. How will I separate into pure water and pure butanol? Can you think about a strategy to separate into pure water and pure butanol? So I have a mixture of water and butanol. Let's say water is 0.2 and 0.8 is butanol, somewhere here. I want to separate into pure water and pure butanol. Again, when I say pure, some people will object. I want water to be 0.9999999999999999999999. When you get tired, you can stop. And I want pure butanol 0.9999999999. So like pure water and pure butanol. Can you think about what to do? Taking advantage of the fact that it splits into two phases. So 0.42, say 0.98, and this one, let's say, is 0.65. Sorry, 0.75. I'll give you 5 minutes to think. So butanol and water form heterogeneous mixture. Heterogeneous means it splits into two phases, one aqueous phase, water rich, and one organic phase, butanol rich. Organic, aqueous phase, organic phase. If the composition is anywhere between 0.42 and 0.98. That is the meaning of the word heterogeneous. I will give you 2-3 minutes to think. Any thoughts from anybody? Hello? Anybody would like to volunteer? Anybody around?
Yes, sir.
Okay. 20 people are around.
Sir, should we use a gravity decanter in this?
तुमको जो यूज करना है यूज कर लो.
So first we start with the distillation column. which
Okay, wait. Let me draw. Okay, what do you want to do with 0.2 and 0.8 mixture?
first distillation.
Distillation, okay. Bottom, what will I get?
Bottom will be pure B, pure butanol.
Okay.
At top it will be azeotrope.
What composition?
Azeotrope at 0.75 water.
Okay, now?
I'm thinking of a gravity decanter next.
Okay, so this is a vapor composition. If I condense this, I will get a liquid which is of 0.75, 0.25, which is in this range of 0.42 and 0.98. So you want to use a decanter.
Yes, sir.
So it will split into an aqueous phase and an organic phase. Organic phase will contain water and butanol. Aqueous phase will contain water and butanol. Okay.
Yes, sir.
Organic phase will contain 0.42. Wait. Organic phase will contain 0.42 and 0.58. Aqueous phase will contain 0.98 and 0.02. Okay, now
Now send the organic phase to one distillation column and the aqueous phase to another distillation column.
अरे बाप रे, एक मिनट हाँ. So organic phase to which distillation column? Another distillation
Another
column.
distillation column, sir.
Okay, so organic phase, I will send it to one distillation column. Okay, and I will do what? I will get what?
So we can recycle the organic phase back to the first distillation.
Aniruddha, let Sharon complete. Then we will see what your idea is.
And at the top, we will get the azeotrope.
Okay, so again water and butanol,
That is
which will
recycled
be
back to decanter.
0.75 and 0.25, which you want to send back to
Send back to
condenser.
decanter. Yeah, sir.
And then the decanter. Okay.
Bottom we will get the butanol.
Water and butanol, so 0 and 1. Okay, and
same for the aqueous phase, like another distillation column, and at bottom we will get pure water.
Wait. Aqueous phase, we go to another column. Now this column we will get water and butanol, 1 and 0.
Yes, sir. Azeotrope
Okay.
at the top, sent back to the condenser.
So 0.75 and 0.25, send it to condenser or have separate condenser. And okay, Aniruddha, what were you saying? Okay.
So the organic phase we can recycle it to the first distillation column.
So what you are saying is, suppose this is column 1 and this is column 2 and this is column 3. What you are saying is column 1 and column 2 are doing the same thing.
Yes, sir.
Okay. Sharon, do you agree?
Yes, sir. So column 2 can be deleted.
But then what do you do with this organic phase?
Send back
this
it,
organic phase,
back
you
to
send
the-
it back to here. Is that
organic phase?
Oh, sorry, not aqueous phase, organic phase. People agree, people disagree. Anybody agrees, anybody disagrees? Anybody agrees, anybody disagrees?
I agree, sir.
Three people out of. Today the graph seems to be like this. Now only 3 people are attending, either physical or mental. Only 3 people are saying something. What do other people say? Do you think this is a good idea, bad idea?
Agreed.
Agreed, sir. Agreed, sir.
Agreed.
Yes.
Agree, sir.
Agreed, it's a good idea.
Okay, okay. So, shall we stop for the day? Shall we stop for the day? What we will do in next class is we have looked at one method of separation, that is without adding third component. So one of the ways was look at pressure if azeotrope composition changes significantly with pressure. Then like this, you see there is a significant change. But suppose with pressure 1 atmosphere or 10 atmosphere, it was not 37.5, but it was still say maybe 75.7 or 75 mole percent. Then there is not significant change. Isn't it? I would not have gone to the other side of the distillation. It is very similar to what this composition is. Or if it was not 77.6, it was maybe 78 or maybe 85, then we would not have been able to go to the other side of the azeotrope, right? Or even in case of THF and water, there is a very significant change with pressure, isn't it? Do you agree with that? So that is one way. If the azeotrope composition changes significantly with pressure, then we can use pressure swing azeotropic distillation. Means have two columns operating at different pressures. Or second, if the two liquid phases, if the two components form heterogeneous mixture which splits into two liquid phases, aqueous and organic, like butanol and water, then we can use two columns and organic and aqueous separator, gravity separator if you like, and two columns like our butanol and water case. Do you agree with this? So we have seen two methods today to separate azeotropes. One is if there is a significant change with pressure, and another if they form a heterogeneous mixture, then we can separate them. Provided the heterogeneous mixture, the azeotrope is between the two heterogeneous compositions.